In the hush of a midnight room, as the ticking clock draws lazy arcs through darkness, a question as old as wonder itself stirs beneath the surface of consciousness. Is time a river in which we drift, or a labyrinth whose passages might be retraced, breached, or even shattered? The roots of this question dig deep, twisting through myth, philosophy, and the hard soil of physics. Imagine for a moment the possibility of slipping the leash of the present, of stepping out of the moment and into the past, or vaulting forward into a future not yet lived. This is the territory of time travel, where Einstein's equations cross paths with the riddles of paradox, and where science, for all its discipline, must sometimes bow before the strange and the unanswerable. The idea of time travel is no recent invention. Ancient tales are woven through with visions of prophets glimpsing futures yet unwritten, of gods who stride through epochs as easily as mortals walk a garden path. The Mahabharata, that vast Indian epic, tells of King Kakudmi, who ascended to the realm of Brahma seeking advice for his daughter's marriage. There, the king waited but a moment in the company of the god. Upon his return, however, he found that ages had passed on earth, empires had crumbled, and all he had known was dust. The Greeks, too, flirted with the elasticity of time, though their visions were more often couched in tragedy and fate than in possibility. Yet it was not until the age of science and the relentless logic of mathematics that time began to reveal its slippery nature. The 19th century birthed a new appetite for the future. In 1895, H.G. Wells published The Time Machine, a novella that would become the urtext of time travel fiction. Wells's unnamed time traveler, with his brass levers and polished crystal, embodied a hope that was also a fear, that history was not immutable, and that the future could be visited, altered, or escaped. The story struck a nerve because it echoed a deeper transformation at work in the fabric of physics itself. The Victorian world was built upon the certainties of Newton, a universe of clockwork regularity, where time moved forward with the inexorable tick of a pendulum, never varying, never doubling back. But that certainty was beginning to splinter. At the dawn of the 20th century, a young patent clerk in Bern, Switzerland, would light the fuse that shattered the Newtonian clock forever. Albert Einstein, with his wild hair and unfashionable shoes, saw what others had missed, that time and space are not separate, absolute entities, but threads of a single woven fabric. In 1905, his special theory of relativity proposed that time is not a universal river, but a current that can flow faster or slower, depending on one's motion. The constant, the unbreakable, was not the tick of a cosmic clock, but the speed of light, 299,792,458 meters per second, a speed that no material thing could ever reach, but which shapes the tempo of reality itself. It was a radical proposition, and it would only grow stranger. According to Einstein, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. The equations are clear and have been confirmed by experiment after experiment. Muons, particles born high in the atmosphere by cosmic rays, should decay in microseconds, never reaching the ground. Yet because they travel at relativistic speeds, their clocks tick more slowly, and they survive the journey to Earth's surface. Astronauts circling the globe at thousands of kilometers per hour experience time at a slightly slower rate than those who remain on the ground, a fact that must be accounted for in the ticking of GPS satellites, lest our navigation systems drift into inaccuracy. This phenomenon, known as time dilation, is the first crack in the wall. It suggests that the future is, in a sense, already accessible. If one could travel at near-light speeds, years could pass for the rest of the universe, while only days or hours elapse for the traveler. The Russian physicist Hermann Minkowski, expanding upon Einstein's work, recast reality as a four-dimensional continuum, space-time, where time itself is simply another coordinate, no more absolute than up or down, left or right. In this view, the past, present, and future coexist, fixed and eternal, and the flow of time is a matter of perspective. But what about the past? Could one, by clever engineering or unlikely accident, return to a moment already lived? Here, science stumbles into paradox. The most famous is the grandfather paradox. If a time traveler journeys into the past and prevents their own grandfather from meeting their grandmother, they would never have been born. So who then made the journey? The paradox is both a puzzle and a warning, a signpost at the edge of reason's map. Yet the laws of physics, stubbornly indifferent to our intuitions, do not always forbid such journeys. In 1949, Kurt Gödel, mathematician, logician, and friend to Einstein, constructed a solution to Einstein's equations of general relativity that described a rotating universe, one in which closed time-like curves could exist. In such a universe, it would be possible to travel along a path through space-time that loops back upon itself, returning to one's own past. Einstein himself was uneasy with this result, remarking to Gödel that such solutions, though mathematically valid, might not correspond to physical reality. Yet the door was open. Physicists have since explored a menagerie of time machines, most of them the stuff of theoretical fancy, but each anchored in real mathematics. The most famous is the wormhole, a tunnel through the fabric of space-time, connecting distant points in both space and time. First described by Einstein and Nathan Rosen in 1935 as bridges, these structures were later named wormholes by John Archibald Wheeler. In theory, if such a tunnel could be stabilized and manipulated, one mouth could be moved at relativistic speeds, creating a time differential between the mouths. Enter the wormhole at one end, and you might emerge at the other, not only billions of kilometers away, but also years or centuries in the past or future. The hurdles are formidable. Wormholes, if they exist, are thought to be unstable, prone to collapse unless held open by exotic matter with negative energy density, matter that, so far, has never been observed. In 1988, Kip Thorne and his colleagues at Caltech explored the requirements for traversable wormholes, showing that the laws of quantum field theory might, in principle, allow for the necessary negative energy, but only in quantities and configurations that seem fantastically improbable. Another proposal, the Tipler cylinder, imagines an infinitely long, rapidly rotating cylinder of dense matter, capable of dragging space-time around it so severely that closed time-like curves form in its wake. The mathematics is elegant, but the engineering demands are impossible by any plausible standard. An infinite cylinder, rotating at near light speed, made of matter far denser than anything in the cosmos. Even were such a cylinder to exist, questions remain about its stability, and about whether the quantum fields that pervade space-time would conspire to destroy any time machine before it could be used. Yet the tantalizing possibility persists. In the quantum world, the realm of the very small, where probability reigns and certainty dissolves, time itself is not quite as inviolable as our senses suggest. In 1976, the physicist Yakir Aharonov and his colleagues formulated the two-state vector formalism, a framework in which the quantum state of a system is determined by both its past and its future boundary conditions. In such a view, the future can, in a sense, influence the past, a subtle statistical echo of time travel. More recently, experiments in quantum entanglement and teleportation have probed the boundaries of causality. When two particles are entangled, a measurement on one seems to instantaneously affect the other, no matter the distance between them, a phenomenon Einstein derided as spooky action at a distance. While no information travels faster than light, the correlations defy classical explanation and hint at a reality where the order of cause and effect is not always so clear. In 2013, Seth Lloyd and his collaborators at MIT proposed a model of post-selected teleportation, in which quantum information could, under special circumstances, be sent backward in time, not in the sense of a macroscopic object traversing centuries, but as a delicate mathematical whisper, a quirk in the machinery of the universe. Causality, the principle that cause precedes effect, is the bedrock of science and everyday experience. If time travel to the past is possible, does causality survive? Physicist David Deutsch, in a 1991 paper, argued that quantum mechanics might resolve paradoxes by allowing for self-consistent histories. A time traveler's actions in the past would always be part of history, never able to create contradictions. If you traveled back and tried to prevent your own birth, you would inevitably fail, or your efforts would somehow become the very cause of your existence. The universe, in Deutsch's view, is a tapestry whose threads cannot be unraveled, only woven in new and unexpected ways. Others, like Stephen Hawking, have been more skeptical. Hawking's chronology protection conjecture posits that the laws of physics conspire to prevent time travel on macroscopic scales, perhaps through quantum effects that destroy any nascent time machine. In 1992, Hawking calculated that the energy fluctuations in quantum fields near a closed time-like curve would become infinite, effectively tearing the fabric of space-time and preventing paradoxes before they could occur. The universe, in this telling, is not so easily subverted. Yet the equations refuse to close the case. In 2009, Hawking held a party for time travelers. He prepared champagne and snacks, and sent out invitations only after the event had already passed. No one came, of course, but the gesture was a playful challenge to the cosmos. If time travel is possible, where are its travelers? The absence of time tourists is not proof against their existence. Perhaps time machines are impossible. Perhaps they are possible, but only in ways we do not yet understand. Or perhaps the universe is stranger still. Perhaps time travelers walk among us, unnoticed, their actions woven so seamlessly into history that we cannot perceive them. The search for time travel is, in many ways, a search for the limits of law. It is a journey through the borderlands of physics, where the familiar dissolves into the uncanny. The equations of general relativity, which govern the large-scale structure of space-time, are indifferent to the arrow of time. They admit solutions, like Gödel's rotating universe or the Kerr black hole, that allow for closed time-like curves. Yet these solutions may be mathematical curiosities, mirages conjured by idealized conditions that never occur in reality. Black holes, those enigmatic punctures in space-time, offer another path to the past, at least in theory. The Kerr solution, discovered by Roy Kerr in 1963, describes a rotating black hole whose interior contains a region where time and space trade places, and where closed time-like curves might exist. Fall into a Kerr black hole, and you might in principle emerge in another era, or another universe altogether. The hazards are formidable. The tidal forces near the singularity would shred any traveler to atoms, and the stability of the region is questionable. But the mathematics whispers of possibilities beyond imagination. The past half-century has seen a flowering of research into the quantum structure of space-time, fueled by the search for a theory of quantum gravity. String theory, loop quantum gravity, and other contenders seek to reconcile the smooth geometry of relativity with the jittery granularity of quantum mechanics. Some of these theories suggest that the fabric of space-time is not continuous, but composed of discrete units, loops or strings vibrating in higher dimensional spaces. In such a universe, the topology of space-time could be far stranger than we imagine, riddled with tunnels, bubbles, and shortcuts that defy classical intuition. Experiments have begun to probe the limits of these ideas. The Laser Interferometer, Gravitational Wave Observatory, LIGO, which detected gravitational waves for the first time in 2015, has opened a new window onto the violent dynamics of black holes and neutron stars. The Event Horizon Telescope in 2019 captured the shadow of a supermassive black hole in the galaxy M87, offering the first direct glimpse of an event horizon, the boundary beyond which time and space are warped beyond recovery. These observations test the predictions of general relativity under extreme conditions, and may, in time, reveal subtle deviations that point toward new physics. Yet the enigma of time remains. The arrow of time, as articulated by Arthur Eddington in 1927, is a puzzle that runs deeper than the equations. The laws of physics are, for the most part, time-symmetric. They do not distinguish between past and future, yet our experience is otherwise. Entropy, the measure of disorder, always increases in a closed system, giving rise to a one-way flow from order to chaos, from memory to forgetting, from birth to death. This thermodynamic arrow is woven into the structure of reality, but its origins are mysterious. Why did the universe begin in a state of low entropy, and how does this initial condition give rise to the inexorable march of time? Cosmology offers some clues. The universe, 8 billion years ago, emerged from the hot, dense state we call the Big Bang. In its earliest moments, matter and energy were distributed with astonishing uniformity, a state of low entropy, from which all structure would eventually arise. As the universe expanded and cooled, pockets of matter clumped together under gravity, forming stars, galaxies, and planets. The increase in entropy was a byproduct of this structure formation, and the arrow of time was set. Yet the question remains, why did the universe begin in such an improbable state? Some physicists, like Sean Carroll, have argued that the answer may lie in the nature of space-time itself. If the universe is infinite, or if there exist many universes, each with its own arrow of time, then our experience may be just one thread in a vast, tangled skein. Others look to quantum cosmology, where the boundary conditions of the universe are determined by wave functions and probabilities, rather than classical certainties. The relationship between time and consciousness is equally mysterious. Neuroscience tells us that the brain constructs a sense of duration from the rhythms of neurons, the firing of synapses, the flow of chemicals and electricity. The present, as William James observed in the 19th century, is a specious present, a window a few seconds wide, within which the mind stitches together the events of experience into a continuous flow. Memory anchors us to the past, anticipation draws us toward the future, but the present is always slipping away, impossible to hold. Time travel, in this sense, is both a physical and a psychological problem. The desire to return to the past, to undo a mistake or relive a joy, is as old as regret. The yearning to see the future, to glimpse what lies ahead, is as old as hope. Science offers the machinery, but the longing is deeply human. Consider the twin paradox, a thought experiment that brings the strangeness of relativity into sharp relief. One twin remains on Earth, while the other embarks on a journey to a distant star at near light speed. Upon the traveler's return, less time has passed for them than for their sibling. The paradox is resolved by the mathematics of special relativity, but the emotional consequences are harder to fathom. Imagine returning to a world grown old, to find that everyone you knew has aged or passed away, that the future is a foreign country. The cost of visiting the future, it seems, is to lose the present. Science fiction has long explored these themes, from Wells's Eloy and Morlocks to the time loops of Groundhog Day and the branching realities of Dark. The stories are compelling because they dramatize the consequences of time travel, not just the technical challenges, but the moral and existential ones. If the past can be changed, what happens to memory, to identity, to responsibility? If the future can be visited, does it become inevitable? And if time is a landscape to be traversed, are we its masters or merely its travelers? Theoretical work continues to probe the boundaries. In 2020, a team led by Germain Tobar at the University of Queensland published a paper exploring the possibility of self-correcting timelines. Using the mathematics of dynamical systems, they showed that, under certain conditions, events would always adjust themselves to avoid paradoxes. The universe, in this view, is a kind of puzzle that solves itself, preserving consistency at all costs. Other researchers have looked to the strange world of closed time-like curves in quantum computation. In 2014, a team at the University of Queensland demonstrated that quantum computers operating with access to closed time-like curves could solve problems that are intractable for classical computers. The logic is subtle, but the implication is profound. The structure of space-time, if manipulated, could unlock computational powers beyond anything we know. Yet the practical obstacles remain immense. The energies required to manipulate space-time are far beyond our current capabilities. The stability of exotic structures like wormholes is uncertain, and the existence of negative energy, or exotic matter, remains hypothetical. Even if time machines are possible in principle, they may be forever out of reach in practice. And yet, in the quantum realm, time is not so straightforward. In 2019, a team led by Gordy Lesovic at the Moscow Institute of Physics and Technology reported a controversial experiment in which a quantum computer appeared to reverse the direction of time for a few electrons, restoring a previous state. The effect was fleeting and confined to the delicate world of quantum information, but it raised intriguing questions about the malleability of time at the smallest scales. Philosophers, too, have grappled with the implications. The block universe view, favored by some physicists and metaphysicians, holds that all moments, past, present, and future, exist equally, fixed in the four-dimensional structure of space-time. In this picture, time does not flow at all. Rather, our consciousness moves along the timeline, giving the illusion of passage. Others argue for a more dynamic view, where the present is real and the future is open, yet to be determined. The debate is far from settled. The nature of time, and our place within it, is a mystery that straddles the boundaries of physics, philosophy, and psychology. Each approach offers insights, but none has yet captured the full strangeness of reality. The paradoxes remain. The grandfather paradox, the bootstrap paradox, in which an object or piece of information is passed from the future to the past, becoming its own origin, and the predestination paradox, in which a time traveler's actions in the past become the very cause of the future they sought to change, are more than puzzles. They are signposts pointing to the limits of our understanding. In fiction, these enigmas become the engines of plot and the seeds of tragedy. In Robert Heinlein's All You Zombies, a time traveler becomes their own mother and father, caught in a closed loop of identity. In Back to the Future, Marty McFly's efforts to save his parents nearly erase his own existence. These stories resonate because they dramatize the stakes of time travel, not just the technical challenges, but the emotional and moral ones. Science, for all its rigor, cannot yet resolve these questions. The equations of relativity allow for time machines, but the quantum world may intervene to prevent their realization. The arrow of time, anchored in entropy, gives direction to our lives, but its ultimate origins remain obscure. The possibility of time travel, like the possibility of faster-than-light travel or teleportation, hovers at the edge of the possible, a tantalizing glimpse of a reality just beyond our grasp. Yet the pursuit is not in vain. The exploration of time in physics and in thought has yielded profound insights into the structure of the universe. The discovery of time dilation, the unification of space and time, the probing of black holes and the quantum fabric of reality, all these advances have been driven in part by the desire to understand time. The journey continues. New experiments probe the limits of causality, the nature of entropy, the possibility of traversable wormholes. The mathematics grows ever more sophisticated, the theories more audacious. Perhaps in time we will discover a loophole, a way to slip the bonds of the present. Or perhaps the universe will remain, as it always has, a place of longing and mystery, where the past is a memory, the future a dream, and the present a fleeting miracle. In the meantime, the clock ticks on. The seconds slip away, the past recedes, the future approaches. We are all time travelers, carried forward by the inexorable flow of entropy. Our memories stretched behind us like the wake of a ship. The questions endure, as urgent and as beautiful as ever. What is time? Can it be traveled, altered, defied? Or is it the one law that cannot be broken, the one mystery that will never yield? The quest to understand time is the quest to understand ourselves. In the equations of Einstein, in the paradoxes of logic, in the rhythms of the heart, we seek not only knowledge, but meaning. The possibility of time travel, whether real or forever beyond reach, is a mirror held up to our deepest hopes and fears, a reminder that the universe is vaster and more mysterious than we can imagine, and that the journey, for all its uncertainties, is worth pursuing. The story of time travel is, in the end, the story of humanity's restless spirit, a spirit that will not be bound by the present, that dreams always of other worlds, other times, other selves. It is a story that will continue, as long as there are minds to wonder, clocks to tick and stars to beckon. The universe, for all its laws and limits, is an unfinished poem, and time, for all its mysteries, is the language in which it is written.